Let's look at the false position method graphically. For any root finding method, we need to have some brackets. We'll talk about open methods next time, but for any method that is sure to find an answer, we need brackets. So we start out with two brackets, x lower and x upper. If we look, we can see that the answer is about x equals 1 is the root. It turns out for this equation, it is the root, but we don't know that right now. We certainly know just by looking at the graph that we've definitely got root bracketed. So we calculate the function at those points, and we got f of x upper and f of x lower. One is above 0, one is below 0. So we indeed have our roots bracketed. Now, if we're doing bisection, then all we need to know is whether f of x upper and f of x lower are positive or negative. From that, we can determine the brackets, and then we could go on, take the midpoint as our new guess, and determine what the new brackets are from the values, from just whether f of x upper and f of x lower are positive or negative. But for false position, we can do a little better, and we actually need those values. So what we then do is we say, well, we're going to say this function looks a lot like a line, and we can get a better guess for where the root is by finding the line, connecting those points, seeing where on that line, what value of x would give 0. And so we go over from f of x equals 0, go down, and there we got a new position for xr. The closer this is to a line, the closer this guess will be to the true root. And so that's what we've done graphically. That's really the method right there. We want to know how we actually calculate that number. So we're going to use some geometry. We've got one triangle here where the base is distance x upper minus x lower, and the height is function of x upper minus function of x lower. And now we've got a second triangle whose base is x upper minus xr, our root guess, and whose height is f of x upper, and base is minus 0. So they're similar triangles, so we can write out an equation that relates the side lengths to each other. The ratio of the side lengths is the same. So that's it. We're just using this geometry, and then we solve for xr, our formula for the root, and we've got it. Remember, the only difference for a bisection method is there that xr is just equal to the average of x upper and x lower. Here, we're approximating it as a straight line, and this gives us our formula. So now we've got that. We've got a guess. We can calculate our new value of f of xr. If it was a line, then we'd get back 0. Linearly, that's what it would be. It's not going to be quite 0, but it should be close to 0 if the function is close to the line. If it's highly curved, then we could get something very different. It might take a long time for this to converge. So once we've got that, then we can start over again. We've got our new brackets. We have to choose whether our new root an xu or xl brackets it. In this case, the root is bracketed by f of xr and f of x upper. And we can tell that because they have different signs. So now we just change that. So now we're at the same situation we were before, except now we've got it bracketed. We draw our line, and we keep on going. You can eyeball it and see that that line is crossing very near x equals 0. The closer we get in, the closer it is to a line. So that's all it is. We just keep on repeating this until our new xr changes by less than our tolerance, and we're done.